We will see the problem. Example 7.3. A circular loop located on x square plus y square is equal to 9. That means it is a circle. You see it's a circular loop. At z equal to 0, carries a direct current of 10 amperes along the A phi, and determine the magnetic field intensity H at 0, 0, 4 and 0, 0, minus 4. So first of all, we will see, we will represent this in a coordinate system. So we have z-axis, x-axis and y-axis. Okay. Now this is a circular loop. You see here the circular loop is at x square plus y square plus z x square plus y square is equal to 9 and z is equal to 0. So it is in the xy plane. It's very clear. So it is very clear that it is in the xy plane. It is in the xy plane. And the equation is x square plus y square is equal to 9. So the radius is equal to square root of 9. So the radius is equal to rho, which is equal to square root of 9, which is equal to 3. So you see here it's x square plus y square is equal to 9. So the rho is equal to root of 9, which is equal to 3. And the current is moving along the along the A phi direction. So it's very clear that the current is moving along A phi direction. This is the direction of the current. So the direction of the current is A phi. Okay. So I will take a small current element here. I will take a small current element here, and this is my small current element dl bar. Okay. So this dl bar is given as dl. That means the magnitudes, its magnitude into direction, and the direction is already given in the problem. You see here it is A phi. Okay, and this is we will use the cylindrical coordinate system for representing this. Now you see, I want to find what is the magnetic field intensity at 0, 0, 4. So let us assume that in general form, let us assume that the point of consideration is like here. It is at 0, 0 at some height h. Okay. So in our problem, actually h is equal to 4 anyway. So that we will come to that later. Now we will see that point of interest is, let's say this is my P. Okay. And let's say this is the point where the current element dl is considered. Let's say this is equal to q. Now I can join this. So this is my vector which is joining the point. Okay. So I can join up to P. So what is my vector R? Actually this is my vector R, is the position vector of P. That means the vector P minus, that is the position vector of P, the position vector of P minus vector Q. So or I can say that the vector R is equal to P, vector P minus vector Q, the position vector of P minus position vector of Q. So before that we will see what is the position vector of P in cylindrical coordinate and what is the position vector of Q in cylindrical coordinates. What is my position vector of P? You see here, in this case actually for P we can say rho equal to 0. Okay, there is some phi we can assume, and z equal to h. Okay, so I can represent this as P is equal to 0, some phi and h. There is no issue. Now I will talk about what is our Q. So what is our Q? Our Q is equal to, you see this is the distance and it is rho. So you have rho, and in this case it is equal to 3. Okay, and there is some phi, you can assume there is some phi here. So there is some phi, and z equal to 0. So my Q can be represented as 3. Okay, or in general I can say it's better to represent in general form. Later on we will substitute the values, rho, phi and z equal to 0. Okay, z equal to 0. Now we will see how to find the magnetic field intensity at this particular point. Okay, at this particular point. So we will take the general equation dH is equal to I dl bar cross the vector r. So this is the direction. Dl bar cross vector r will be the direction, and divided by 4 pi, okay, into the magnitude of vector r whole cube. Okay, so we got vector r now. Vector r we got it, that is vector p minus vector q. So r is given as, you see here, 0 phi h 0 phi h minus rho phi 0, okay, rho phi 0. So vector r is given as 0 minus rho, it is rho minus rho, and what is the direction? It is a rho, because we know that the direction of the rho, this is the direction of the rho, which is a rho, okay, a rho. Then phi minus phi is equal to 0, then h minus 0, that is h, so plus h into az. So this is my vector r, okay. Now we want to find what is our dl bar. Dl bar is equal to dl, I told you, the length with the direction. The direction is a phi, because whenever something is rotating, you know, this long x axis, you saw this is rho and this is phi. So this is the direction of that rotation, that is a phi. So this is a circular loop, so this is the direction a phi, okay. Now we will see what is dl. So what is dl in terms of cylindrical coordinates? So we have taken a small piece here, so we will find that dl from this. So what is our dl? You know, suppose I take a small piece, you see this is the circular piece, so this is small angle is d phi and the radius is rho, okay. So if I want to find dl, you know that angle is equal to arc over radius, okay. So what is our arc? Our arc is dl, this is the small distance dl divided by the radius, that is my angle d phi, okay. So I can find my dl is equal to rho into d phi. So I hope this is clear to you. So it is nothing but rho into d phi, okay. So my dl, what is dl? Okay, what is dl? That is dl is equal to rho into d phi. So I can represent my the vector dl bar, which is equal to dl into a phi, which is equal to rho into d phi into a phi, okay. So now I got it. Now what is my vector r cube? So I got now what is dl bar, what is dl, so I got this one. Now I want to find what is vector r cube. So we will see now vector r cube, vector r magnitude cube, this is equal to, you see what is vector r, so this become minus of rho square, so minus of rho square is rho square plus h square whole power 1 by 2, then power 3, so this become whole power 3 by 2. So this is my vector r cube, okay. Now I got everything, I got dl also. Now we will substitute it in this equation, so we get our dh is equal to I by 4 pi, okay. The magnitude of r cube is nothing but rho square plus h square whole power 3 by 2. Then we will see dl cross r. What is our dl? dl is equal to rho into d phi into a phi. So rho into d phi into a phi cross, okay. Then what is our r? r is equal to minus rho a rho minus rho a rho plus h into az, h into az, okay, h into az. So we will find the cross product. So how to find the cross product? So we will see we have we have the cylindrical coordinate system. It contains rho, phi. So it's nothing but the unit vectors are a rho, a phi and az. So we will move like this. This is the order. Now you see the first term. The first term is a phi and a rho. So a phi and a rho. That means I have to move back. so I have to move back. So this is a phi and this is a rho, so that will be minus az. So a phi cross a rho is equal to minus az. So we have to substitute this in above equation. So what we will get, so dH is equal to I over 4 pi, okay, then rho into d phi is there, then already there is a phi and a rho, this become minus az, and there is a minus here, so this become plus, so and there is a rho here, so this become rho square, and a phi cross that become az, so here we will get the total result like this. Okay, I hope it is clear to you. Then we have, what is there, so I will just put the denominator also, square plus h square whole power 3 by 2. Then next you see here there is a phi, then what is there, az, so phi and z, so if it is phi and z, the result will be a rho, so a rho, we will get the result in terms of a rho. Now there is h, okay, h is there is rho, then there is also d phi, okay, and it is also plus sign. I hope it is clear. So this the final result will be like this, but you have to know that we are considering a symmetrical system now. So let us redraw it again. So x, y and z. Now suppose this is your circle. You see, due to this there is a component which is acting in this direction. I can split it into two components, okay, and this is our h or dh. So dh in the direction of rho and dh in the direction of z, okay. So what will happen, due to the symmetrical nature of this problem, you see here something which is opposite on the other side will also give you something in this direction, okay. This is your dh, it is also having the same component because the current is same, and this will get also added up, okay. So what is going to happen is that the a rho component, the component in the direction of rho, will cancel each other, okay. So finally we will end up with only the z term, okay, that's z term with az term only. So we will be doing only the integration only for the z term. So we can write our dh as I by 4 pi, then rho square plus h square whole power 3 by 2, okay, then rho square d phi az, rho square d phi az, like this, because the other term cancel. So total integral effect will be equal to 0. So total will be equal to 0. So how we will find the h? So how to find h? H is equal to integral of dh. So this integral of 0 to 2 pi, because the only variable is phi. Phi changes from 0 to 2 pi. So h is equal to integral 0 to 2 pi. So this is I over 4 pi, okay, then rho square plus h square whole power 3 by 2, then there is a rho square here, then integral of d phi is 2 pi, then az. Now we can cancel the terms. You see, this is 2 pi, this is 4 pi, and this become 2. So we will get the answer as I over 2 into rho square into az divided by rho square plus h square whole power 3 by 2. So I will write the final equation again. H is equal to I into rho square into az divided by 2 into rho square plus h square whole power 3 by 2. Okay. Now we will see, we want to find what is the magnetic field intensity at 0, 0, 4 and 0, 0, minus 4. That means in our case we want to find H at 0, 0, 4 and H at 0, 0, minus 4. So what is the only variable which is changing? That is nothing but H. So this is H. So here H is equal to 4 and H is equal to minus 4. But in the equation you have seen the final result contains H square. Okay, so the intensity is like minus 4 square in one case, and another case it is like 4 square. You see, if I put it the value for H, so H at 0, 0, 4 is equal to H at 0, 0, minus 4, because the final equation contains H square. So if you square minus 4 and 4, you will get the same answer. So this become I into rho square into AZ divided by, so what is I? Okay, I will substitute. Okay, I will substitute again. I will just give the formula again, plus AZ divided by 2 into rho square plus H square whole power 3 by 2, which is equal to, what is I? Okay, let me check what is I forget. Okay, we'll see the question. Okay, 10 ampere. So 10 ampere. And what is the radius? It is nothing but 3 square. So the radius is 3. So 3 square into AZ divided by 2 into, this is like 3 square plus H square, that's minus 4 or 4, whatever it may be, whole power 3 by 2. Okay, so this is the final answer. So you will get the answer as H is equal to 0.36 AZ ampere per meter. So you see here this H is in the direction of Z. So let us see now the beauty of this problem. Let's just consider this loop again. Okay, since I am considering here H is equal to I over 2 then rho square AZ divided by rho square plus H square, okay, whole power 3 by 2. Now if you see the components, I told you if you have components like this, the components can be splitted. This is your DH due to the current element DL bar. So the component of H can be splitted into two components, one in the direction of rho, that means it is AH rho, and the other components in the direction of Z, that is the HZ. Due to the symmetrical nature, it will cancel. Okay, that's why we don't have the rho component. So if you take the current loop, in this case, this is the current loop, your DL, and if you take here this point at the center, you can see that the magnetic field is going like this. So this is the nature of the magnetic field. But suppose you consider another point somewhere here. Now due to this, you see here there will be magnetic field intensity DH, and this DH is having, anyway I will call this DH and this is DHZ. So I have the component DH rho in this direction, and in this direction I have DHZ. Now if I take the symmetrical part of this, okay, you will see that this will not cancel. You see, this will give you another component, this will give you another component, and the direction of the current is like this. So it will give you some component which is not same. That means that you can see that this HZ component will get added up, but this DH rho component will not cancel. So what you will see that if you take any point here, you will be having a small bending here, you see. So the magnetic field will be like this. So the horizontal components will not cancel. Okay, the horizontal components will not cancel. So this is the nature. So I hope this part is clear to you. So towards the edges you will see more bending. So if you see, this is you can have more bending. Okay, you can see more bending. And you know the magnetic field, the divergence of the magnetic field will be equal to 0. That means it will be a closed loop like this. Okay, so this is the magnetic field around the current carrying loop. Okay, this is how you are getting the magnetic field. So I hope this part is clear to you. Thank you.